We're going to look at Lewis structures, and this is quite a long video because it's going to explain the Lewis structures of covalent compounds, which is a very important topic in general chemistry, and you'll use again all the time in organic chemistry. Writing Lewis structures takes practice, so it's important that after you use these videos, you actually practice writing several of these, and the Alex homework can help with that, and among other things. So here we want to first look at Lewis structures of atoms, then Lewis structures of ions, and then finally Lewis structures of covalent compounds, which is the bulk of this material. Here we will also cover formal charges because formal charges are essential for writing Lewis structures of covalent compounds, even though they're covered in the next section. So in the next section we'll skip the formal charges and we will cover them here. So let's look at the Lewis structures. Before we look at Lewis structures, what we need to remember is valence electrons. Valence electrons are the outermost electrons, and they're known by their A group number. So 1A, 2A, 3A, 4A. 1A has 1, 2A has 2, 3A has 3, 7A has 7, 8A has 8. So if we want to draw the Lewis structure of atoms, which you've actually seen before, such as carbon, carbon is in 4A, so it has 4 valence electrons. We would draw that like this. So 4 dots. We essentially consider 4 quadrants. 1, 2, 3, 4. The top, the right, the bottom, and the left. If we wanted to draw fluorine, we would draw the 4 dots, but we need a total of 7, so we draw 5, 6, 7. So that's the Lewis structure of fluorine. Or if we wanted to draw boron, which has 3, we would draw boron 3 like that. It's also important to note that in the same group, they have the same number of valence electrons. So you'll remember lithium, sodium, potassium, and so on have the same or have similar chemical properties. And the reason for that is they all have 1 valence electron. So lithium is this, sodium is this, potassium is this. So now that we've drawn the Lewis structures of atoms, well, let's look at ions. So, for example, if we wanted to take lithium plus, well, lithium is then missing this electron. So this is lithium plus. And if we wanted to take fluorine and make it minus, instead of fluorine having 7 valence electrons, it would have an extra electron, or it would have an 8th, or said another way, it would be isoelectronic with neon. So we would draw 1, 2, 3, 4, 5, 6, 7, 8. And then we could put a minus charge like that. And this lithium plus and this F minus could be attracted to each other. Lithium fluoride. Or we could have magnesium, which likes to be 2 plus in ionic compounds where it loses its 2 electrons. So now it's 2 plus. And we could have it interact with oxygen, which likes to be 2 minus. I'm just going to circle it like that, which now instead of 6 valence electrons has 8 valence electrons, or is full, or is noble gas-like. And then these two things can be attracted to each other. So again, valence electrons are the outermost electrons in an atom. Also, what is important to note is that if something becomes negatively charged, it gains valence electrons. If something becomes positively charged, it loses valence electrons. Usually all of those valence electrons, because stable ions tend to be isoelectronic with noble gases. So this would have lithium would have no electrons in n equals 2. It would only have the 2 electrons in n equals 1, and those aren't really valence electrons, so we don't draw them. So this is how we draw Lewis structures for atoms and ions. In the next section, we're going to look at drawing Lewis structures for covalent compounds, which is a little bit different. In a covalent compound, electrons are shared instead of transferred. And there are 4 fundamental rules that we will cover. The next video, or this next section of this video, is quite long. And it's very important to take notes and to practice with this stuff. In this series of videos, I'm going to go over how to draw Lewis structures. It's really important that if you're watching this, you treat this like a lecture. So you have paper out, a notebook, and you take notes as you go. And you practice writing them down as we go through the examples, because it's really important to have that practice. And if you just watch it passively, it won't be the same experience as if you were, say, in a class and I was going over a similar material. So there are 4 steps, essentially, to writing Lewis structures. And I strongly recommend right now you pause the video and you write down these 4 steps that we'll go through just now. So, step 1, count the valence electrons. Remember that the valence electrons are attached to the A group number. So, for example, carbon's in 4A, so it has 4 valence electrons. Nitrogen's in 5A, so it has 5. Oxygen, sulfur, selenium are all in 6A, so they have 6. Fluorine, chlorine, bromine, iodine are in 7A, so they have 7. Note that I didn't mention like silicon has 4 or phosphorus has 5. So this is basically how it works. The other nonmetal that comes up, because we're going to draw Lewis structures for covalent compounds between 2 nonmetals, is hydrogen. And hydrogen's in 1A, so it has 1 valence electron. So just use your periodic table to help you count the valence electrons. Next, put the least electronegative atom in the middle. If you remember our trend for electronegativity, so if this is increasing electronegativity, the trend is up and to the right. Said another way, fluorine is the most electronegative atom, followed by oxygen, followed by chlorine. And if we look at it on a periodic table, fluorine is the most electronegative, followed by oxygen, followed by chlorine. So these are the most electronegative atoms. You want to put the least electronegative atom in the middle. Almost always, but not always, the least electronegative atom is written first. However, that's not always the case, so just remember, put the least electronegative atom in the middle. Next, fill octets. So essentially, atoms bond so that they'll be more noble gas-like. The noble gases have 8 valence electrons. So, in covalent compounds, molecules will share electrons such that they have 8. This is a hard concept to visualize. It's much easier to see through example, and we're going to go through several examples in this series of videos. So, we'll go through them, and we'll talk about what it means to fill the octets as we do the examples. Points A and B will come up in certain cases. Okay, use multiple bonds if you don't have enough electrons. We'll discuss that when we get to it. Expand octets if you have too many electrons and the atom is period 3 or lower, and that means lower on the periodic table. And again, we'll explain that when we get to it. And then finally, minimize formal charges. Formal charges are an electron counting system that allows us to know which atoms are charged. So you'll recall that if an atom has more electrons than it wants, it's negatively charged, and if it has less electrons than it wants, it's positively charged. The same rules apply for covalent compounds, and we'll look at that as examples as well. So these are the basic rules that we will use for counting, for making Lewis structures. Using these 4 rules repeatedly will allow you to see some patterns, which is great. However, if I just teach the patterns, it'll be a lot of memorization. If you follow these 4 relatively simple rules, you'll see the patterns for yourself. And when you see them, great, use them. But until then, follow these 4 rules and you'll be good to go. Now let's look at a first example. So the first thing that I want to draw the Lewis structure of is F2. If you haven't already done so, please pause the video and write down the 4 rules. Also note that as I go through these examples, it's really important to have a pen and a paper out and to follow along, take notes as if you were watching a lecture instead of just watching a computer screen. So it's really important to do that. So, step 1, count the valence electrons. Well, fluorine's a halogen, as you probably know, so it's in 7A, so it has 7 valence electrons. There are 2 of them, so we have 2 times 7, which equals 14 electrons. So we have 14 valence electrons to consider. Step 2, put the least electronegative atom in the middle. Well, in order to have a middle, you'd have to have at least 3 atoms. And in this case, we only have 2 atoms, so there is no middle. So we simply start by bonding a fluorine to another fluorine. This is where we begin. Next, fill octets. Okay, counting in eights will help you save counting time, but is not absolutely required. But let me show you what I mean. So far, I've used 2 electrons. This bond represents 2 electrons. So I have 12 electrons left. If I want to fill octets, I can put 2, 4, 6 more electrons around this fluorine, and 2, 4, 6 electrons around this fluorine. So that's a total of 2, 4, 6, 8, 10, 12, 14, all 14 electrons. I'm going to draw this a little bit differently. But before I do that, I want to do some nomenclature stuff. This is called a covalent bond. More specifically, it's called a single covalent bond. These, all of them, I'm only going to put an arrow to this one, is called a lone pair. Note that the term is lone pair. They come in pairs. They should not be single electrons. They always come in pairs. It's not 100% true 100% of the time. There are such things as free radicals, and they do exist, but generally speaking, they come in pairs. Free radicals are very unstable molecules, so they come in pairs. So we have these covalent bonds, and we have these lone pairs, which again come in pairs, which are 2 dots. I want to write this a little bit different of a way, just because it's a little bit easier to see. This is not typical nomenclature, and I'm only doing it for example purposes. However, if we have F, and I write this instead of a dash as 2 dots, because it is 2 electrons, and I have another F, and then I put the lone pairs all around this, like this, this and this are the same representations. Okay, except we have the dash as the 2 electrons, which is a much more typical way of writing it, and that's the covalent bond. But now I've here just put the 2 electrons between the 2 atoms. If I hold my finger over this fluorine, you can see that this fluorine is noble gas-like. It has 8 electrons around it, which is why it's called the Octet Rule. All right, so fill octets means put 8 electrons around it or make it noble gas-like. If I cover up this fluorine, you can see that this other fluorine has 8 electrons around it. So by fluorine sharing 2 electrons between them, you have a situation where both fluorines are now noble gas-like. Just like in ionic compounds, where one thing gains an electron or more electrons, and another thing loses electrons so that both are noble gas-like, in covalent compounds, they share so that both are noble gas-like. So now we have a beneficial situation for these 2 fluorines, and this is great. We have now filled the octets of both, so we count this as 2 electrons, so 2, 4, 6, 8 electrons around this fluorine, 2, 4, 6, 8 electrons around this fluorine. They're both noble gas-like, they both have full octets. We don't need to do step A or B here, because we fortunately, or because we picked a straightforward example to begin with, we have the octets filled. Last step, minimize formal charges. For the first several examples that I do in this video series, we will not be minimizing formal charges, we'll be simply calculating formal charges. Formal charge is essentially looking at the number of electrons around an atom. So let's see what we do. This is a little bit confusing because for Octet Rule, we consider this as 2 electrons for the exact reason that this is noble gas-like and this is noble gas-like. However, for formal charge, we consider that one of these electrons formally belongs to this fluorine and one of the electrons formally belongs to this fluorine. So if I just kind of put a circle around it like this, you can see that for formal charge purposes, one of the electrons belongs to this fluorine, and one of the electrons belongs to this fluorine. So essentially, I'm counting this as 1 for this fluorine and 1 for this fluorine. Now, in your book, you'll learn this formula. Formal charge equals valence electrons minus half bonding electrons minus lone electrons. And this is 100% true. Okay, this will work every time. However, in my opinion, this is a very long way of doing it. In this case, we only have 2 atoms that are both the same, so this isn't going to take very long. But if we have, 6 or 7 atoms, then some of them are not the same. This can be very time-consuming. So there's, in my opinion, an easier way to do this. Let's just consider how many valence electrons fluorine has. Fluorine, as we said right at the beginning of this discussion, has 7 valence electrons. So fluorine wants to have 7 electrons around it. Remember that in a bond, we have 2 electrons, but formally, one belongs to this fluorine and one belongs to this fluorine. Said another way, count the dash as 1, because it's 1 electron for this fluorine, and you'll count it as 1 for this fluorine. Count the dots as 1, because this is an electron that truly belongs to this fluorine. So fluorine wants to have 7 electrons around it. How many does this fluorine have? Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5, 6, 7. If fluorine wants to have 7 electrons around it, has 7 valence electrons, and has 7 electrons around it, it's neutral. This fluorine's the same. It wants to have 7 electrons around it. Count the dots as 1, count the dashes as 1. 1, 2, 3, 4, 5, 6, 7. Wants 7, has 7. It is neutral. When it says minimize formal charges, 0, neutral, is the minimum. All right, so this doesn't mean the largest negative number. It means make the formal charges 0. In my opinion, minimizing formal charges is the step at the end that allows you to check your answer. If you have filled the octets and all the formal charges are 0, chances are you have drawn a great Lewis structure. And here we have a good Lewis structure. This is the correct Lewis structure of fluorine. I'm going to stop the video here and continue with a second video on the same playlist. In the previous video, I gave one example of a Lewis structure and went through these 4 rules. It's a really good idea to watch that video first. If you've already watched that video, you still want to have a pen and paper out and take notes as if this is a lecture. It's really important that you actually practice writing these things out, and simply watching the video passively may not be enough. Furthermore, after you've seen these videos, it's really important to try some examples. Alex can give you practice on this if you're looking for a place to practice. So in this video, I want to draw a few more Lewis structures. I want to start with CH4. So when I'm drawing the Lewis structure for CH4, which is methane, my first job is to count the valence electrons. So carbon has 4, it's in 4A, plus 4 times 1, there are 4 hydrogens, each with 1 valence electron, for a total of 8 electrons. So I did step 1, count valence electrons. I found that there's 8 valence electrons. Put the least electronegative atom in the middle. Well, hydrogen is less electronegative than carbon, but hydrogen never goes in the middle. So we have no choice but to put carbon in the middle. Most of the time, not always, the atom that goes in the middle is written first. Sometimes it doesn't, and that is not the case, but most of the time it is the case. So we put carbon in the middle, and we simply bond it to 4 hydrogens, like so. Fill octets. So octets make atoms noble gas-like, except hydrogen. Hydrogen doesn't want an octet. It wants to have 2 electrons around it, like helium. Remember that in each of these covalent bonds, there are 2 electrons. So hydrogen has 2 electrons around it, like helium. It's happy. Carbon has 2, 4, 6, 8 electrons around it, like its nearest noble gas. Neon, so it's happy. So this looks like a pretty good start. As I mentioned in the previous video, step 4, minimize formal charges, is really a way to check your answer. Remember that minimize formal charges doesn't mean make them as negative as possible. It means make them 0 if possible. So we want to try to make the formal charges 0. Well, let's calculate the formal charge for carbon. Remember that there are 2 electrons in this bond, but formally 1 belongs to carbon and 1 belongs to hydrogen. Said another way, count the dashes as 1. If there were lone pairs, you would count each dot as one individual electron. So carbon has 4 valence electrons. It wants to have 4 electrons around it. How many does it have? Count the dashes as 1. 1, 2, 3, 4. Wants 4, has 4. It's neutral. Hydrogen wants 1 electron around it. It has 1 valence electron. Count the dashes as 1. It has 1 electron around it. It's neutral. These 3 hydrogens are all the same. Everything is neutral. We have the octets full. This is a great Lewis structure. So we're pretty much done with this. There's one other point to make about formal charges. The sum of the formal charges should add up to the sum of the charge on the species. Said another way, overall CH4 is neutral. So the sum of all the formal charges on the atoms should add up to 0. In this case, they do, because carbon is 0 and hydrogen is 0. Let's look at another example that at first may seem somewhat more complicated. Let's do CF4, a similar molecule to CH4. So in this case, we have 4 plus 4 times 7 valence electrons. So we're doing step 1, counting the valence electrons. Carbon has 4, fluorine has 7, and there are 4 of them, which gives us a total of 32 electrons. 28 plus 4, 32 electrons. Put carbon in the middle, because it's the least electronegative atom. Bond it to 4 fluorines, like so. We have now used 2, 4, 6, 8 electrons, which means we have 24 electrons left. Another way to do this is to simply fill the octets of all the fluorines. So if I fill the octets of all the fluorines by putting 1, 2, 2, and 2, 3 lone pairs, so for a total of 2, 4, 6, 8 electrons around this fluorine, if I do that 4 times, that's 32 electrons. Counting by 8s, although not required for doing Lewis structures, does save you time in counting. So if I put 8 electrons, 1 bond and 3 lone pairs around each of the fluorines, that will be the 32 electrons, because 4 times 8 is 32. So it just saves us time from counting all the electrons. However, remember to count this as 2, and these are each 2, of course. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. You can do it that way as well. Now, we've filled all the octets. We've used the 32 electrons that we have available. So this looks like a pretty good Lewis structure. But we still have step 4, which is minimize the formal charges. Remember that this is kind of like a check on your work. So we filled all the octets. If all the formal charges are 0 and the overall charge of the species is 0, we have a good Lewis structure. So let's see. Fluorine wants to have 7 electrons around it. Count the dots as 1, count the dashes as 1. Remember, there's 2 electrons in the covalent bond. 1 formally belongs to this fluorine and 1 formally belongs to carbon. So we're going to count the dots as 1 and count the dashes as 1. Fluorine wants to have 7 electrons around it, and it has 1, 2, 3, 4, 5, 6, 7. If something wants 7 electrons and has 7 electrons, it's neutral. Carbon wants to have 4 electrons around it. Said another way, carbon has 4 valence electrons. How many electrons are around this carbon? 1, 2, 3, 4. Wants 4, has 4, it's neutral. At first, CF4 seemed like a significantly more difficult Lewis structure than CH4, because it had 32 electrons instead of 8 electrons. But by following these rules, we very quickly found the correct Lewis structure. In fact, after we did step 3, fill the octets, we were essentially done. We didn't have to do any work to minimize formal charges. We just calculated them, they're all 0, and we're done. So if you follow the rules, this will be very helpful, and you'll start to see patterns in your work. I do want to do one more example for this video, and that example is going to be water, H2O. When I want to draw the Lewis structure of water, I now need to start by counting the valence of electrons, just like in every other case. The rules you'll memorize very quickly because you use the same rules every single time. So in this case, I take 2 times 1, because there's 2 hydrogens, each with 1 valence electron, plus 6 for a total of 8 valence electrons. Put the least electronegative atom in the middle, except hydrogen. And this is kind of a double exception because hydrogen is actually written first. Generally, you put the atom written first in the middle, but in this case, we have to put oxygen in the middle because hydrogen never goes in the middle. So we put oxygen in the middle, and we bond it to 2 hydrogen atoms. We now have used 2 4 electrons. We have 4 more electrons to place, and we have to decide where to put them. Do we put them around hydrogen, or do we put them around oxygen? Well, we choose to put them on oxygen because our job is, step 3, fill octets. So, everything wants an octet except hydrogen. Hydrogen only wants a duet, if you will, so it can be like its nearest neighbor, helium. So hydrogen's already happy, but oxygen only has 2 4 electrons around it. It's not noble gas-like, but I have 4 more electrons, so what do? I put 2 lone pairs like this. I've now used 2, 4, 6, 8 electrons, and I've filled the octet of oxygen. I filled the duet, if you will, of hydrogen because it has 2 electrons around it and it wants to have 2 electrons around it. So seemingly, I have done step 3. Step 4, again, minimize formal charges, is a check on the system. So basically, I can see if my decision to put those extra electrons around oxygen was a good one. Well, if the formal charge is 0 on everything, that's a good decision. I should know the formal charges are not always 0, and we'll get to some examples in a later video where formal charges are not 0. But here, let's take a look. So, hydrogen wants 1 electron around it, count the dashes as 1. 1 has 1, wants 1, has 1, it's neutral. Oxygen has 6 valence electrons, so it wants 6 electrons around it, count the dots as 1, count the dashes as 1. 1, 2, 3, 4, 5, 6. It wants to have 6 electrons around it. It has 6 electrons around it. It is neutral. All the formal charges are 0. Note this hydrogen and this hydrogen are the same, so all the formal charges are 0. And this is a great Lewis structure, the correct Lewis structure for water. I'm going to stop the video here, but in the next video in the series, I will go over some more examples. In the previous videos, I went over some of the basic rules for drawing Lewis structures. In this video, I'm going to continue to apply these rules to draw the Lewis structures of things in different situations. In this series of videos, I'm going to try to give you examples of many different situations you can encounter, but it is absolutely essential to practice. Also, if you're watching this video and you haven't already, please have out a notebook and some paper and take notes as you go. It's really important to treat these videos like a lecture, where you're actively learning and engaged in the process, instead of simply passively watching it. I don't think you'll get a lot out of it if you just passively watch the video. So let's continue with a few more Lewis structures in this video. Specifically, we'll go over 3 examples. So, the first one I want to do is oxygen, diatomic oxygen, O2. So by now, you're probably already familiar with the first step, which is count the valence electrons. So we have 2 oxygens, each with 6 valence electrons, which is a total of 12 electrons. So we have 12 electrons that we would like to place. Put the least electronegative atom in the middle, except hydrogen. Well, we only have 2 atoms, so there's no atom in the middle. So we put O bonded to O. We have now used 2 electrons, which means we have 10 left. I want to fill octets. So 2, 4, 6, 8, 10, 12. Uh-oh. I can't fill the octet because I've run out of electrons. 2, 4, 6, 8, 10, 12. I've placed 12 electrons, and this oxygen has an octet, it's happy, but this oxygen does not have an octet. This is where we need to go to these subrules, and specifically subrule A. Use multiple bonds if you don't have enough electrons. Now over the years, one thing that I've seen the students do is, when they get to this point, they start over. That is a bad idea. Okay, you don't want to start over. You want to use the rules to fix what you have and make it into a proper Lewis structure. So we have to make a multiple bond. Well, how exactly do we do that? Well, what we need to do is take one of these lone pairs and move it into a bonding pair. And of course, we have two choices for doing that. And because this is the first time we've seen multiple bonds, I do want to go into detail on those two choices. So what I'm doing right now is simply rewriting what I've had in the past. So my first choice is I could take these two electrons and move them into a multiple bond. My second choice is that I could take these two electrons and move them into a multiple bond. So in this case, I have O. I'm going to try to leave them in the same spatial arrangement. Note that that doesn't really matter because in real life they don't orient themselves like they will on a piece of paper, because a piece of paper is a two-dimensional space and real life is a three-dimensional space. But just for clarity, I want to move these two electrons into a double bond. And in this case, I want to move the other two electrons into a multiple bond. So I move these two into a multiple bond, so they're gone. And I still have the bonds like this. So I had two choices of how to make the double bond. I needed the double bond because I didn't have enough electrons to fill the octet. Note that I can't just simply add two electrons. Okay, that is just making electrons appear. This is not magic. We can't do that. So we had these two choices for making the multiple bonds. Which is better and why? Well, in the first case, there's 2, 4, 6, 8 electrons around this oxygen, and 2, 4, 6, 8 electrons around this oxygen. That's pretty good. In the second case, there's 2, 4, 6, 8, 10 electrons around this oxygen, which is actually a violation of the Octet Rule, which oxygen is too small to do. Instantly bad. 2, 4, 6 electrons around this one. This doesn't have an octet. So this choice is clearly the better choice. So when given a choice of which electrons to move, you generally want to move the one from the atom that already has an octet. So this was a better choice. Note that as you practice this and you make this wrong choice, if you accidentally make this wrong choice, you can check yourself and see if it was the correct choice. And by counting the octets, you find out very quickly that it wasn't. Just go back where you started and try the other side and see if that works out better. This is a kind of a guess and check methodology and understanding which one follows the rules more correctly. And in this case, it's clearly this one that follows the rules more correctly. As you progress through this and you do more and more examples, you'll start to see some patterns. And that's great. Once you see those patterns, use them. But until then, follow the rules. So now we have 2, 4, 6, 8 electrons around this one, 2, 4, 6, 8 electrons around this one. Everybody's happy. Minimize formal charges, which, as you'll recall from the previous videos, I really think is a way to check your answer. So let's see what the formal charge is. Oxygen wants to have 6 electrons. Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5, 6. This oxygen is neutral. This oxygen is the same. 1, 6 electrons has 1, 2, 3, 4, 5, 6. Great. We have the right Lewis structure. This is the correct Lewis structure. The next example I want to go over is another very famous molecule, carbon dioxide. Count the valence electrons, 4 plus 2 times 6, which is a total of 16 electrons. So put the least electronegative atom in the middle, carbon, bond it to an oxygen, bond it to an oxygen, and I notice that if I fill the octet of both of the oxygens, I will have used 16 electrons because 2, 4, 6, 8, and the other 2, 2, 4, 6, 8, 2 8s is 16. Again, if you want to just count them 2, 4, 6, 8, 10, 12, 14, 16, that is a perfectly legitimate thing to do as well. So I filled the octets of oxygen, but I haven't filled the octets of carbon. So you'll see that I have two choices here. And I want to clearly illustrate the two choices because it's the first time doing examples like this. So I'm just rewriting exactly what I had, which is placing the 16 electrons, like so. And I again realize I filled the octet of oxygen, but carbon only has 2, 4 electrons around it. So oxygen has an octet, carbon only has 4. These are identical. So I have two choices. One double bond isn't going to be enough. Okay, because that'll only put 6 electrons around carbon. So in this choice, I'm going to take 2 electrons from this side and 2 electrons from this side and make 2 double bonds. Let me show you what that looks like. We have C double bond C, O double bond C, double bond O, and we have the 2 lone pairs on each oxygen. So again, I simply move this lone pair into a double bond. As I said in the previous example, when I see that this is incorrect, I don't start over. I've already done a lot of work. I don't want to start over. What I want to do is fix what I have and make it follow the rules. I want to fill the octet. I'm working on rule 3. I didn't fill the octets here, so I moved those into a double bond, and that filled the octets. In this case, I want to do the opposite. I don't know if it's the opposite, but I want to do something different. I want to take both electron pairs and put them on this oxygen. So what I end up with is not a double bond, but a triple bond. O, triple bond C, bond O. Whoops, let me just, I apologize, that's not real clear, but I want to put the lone pair here, just so it's in the same place. So I took these 2 electrons, double bond, triple bond, and I have these 2 cases. In the previous example, when I picked from one side or the other, one had all octets and the other one didn't, and that's how we eliminated it. But in this case, we don't have that. We have 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 around carbon, and this oxygen's the same, 2, 4, 6, 8. Good. Octets are full. In this case, I have 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 electrons around carbon, and 2, 4, 6, 8 electrons around oxygen. Octets are full. Well, how do we know which of these 2 things is better? Unfortunately, Octet Rule is not the solution to that problem. In this case, the solution to that problem comes in step 4, minimize formal charges. Well, the first step to minimizing formal charges is calculating the formal charges. So let's take a look. Oxygen wants to have 6 electrons around it. Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5, 6. It's neutral. And this oxygen's the same. 1, 6 has 1, 2, 3, 4, 5, 6. It's neutral. So both oxygens are neutral. What about carbon? Carbon wants to have 4 electrons around it, and it has 1, 2, 3, 4. It's neutral. Great. So both the oxygens and the carbon, or all the atoms said another way, are neutral. That seems pretty good. How about this one? Oxygen wants to have 6 electrons around it. This oxygen has 1, 2, 3, 4, 5. It's missing an electron. Something that's missing an electron has a positive charge. Because electrons are negative, so if it's missing 1, it wants 6, it only has 5, it's going to be positive. How about carbon? It wants to have 4, it has 1, 2, 3, 4. It's neutral. How about this oxygen? It wants to have 6, and it has 1, 2, 3, 4, 5, 6, 7. It has an extra electron. Something with an extra electron is negatively charged. Notice that in both cases, the sum of the formal charge, here they're all 0, equals the charge on the species, and this overall carbon dioxide is neutral. Here you have a plus and a minus, and the sum of the formal charges still equals neutral. It's just another check that you counted the electrons properly. However, in this case, there's a clearly better Lewis structure. This is a better Lewis structure because it has minimal formal charges. The formal charges are closer to 0. This is a worse Lewis structure because it has a minus formal charge and a plus formal charge. So this is the worse Lewis structure. This is the better Lewis structure. I do want to quickly go over one last example that illustrates a different point. In this case, I have a very notable compound, XeF2. And what's notable about XeF2 is it's got a noble gas. This, or XeF4, was one of the first discovered noble gas compounds because someone realized fluorine is super reactive and they mixed it with xenon gas and they were able to actually isolate a compound. I believe this happened in approximately the 1970s. So this compound does exist, but it is notable because it does contain xenon, a noble gas. Well, let's draw the Lewis structure for it. First step, of course, is counting the valence electrons. So we're always following these 4 rules. All right, these 4 rules will lead us to the best Lewis structure. So we have XEF4. So we have 8 plus 2 times 7. That'll be 14 plus 8, which is 22 electrons. We put xenon in the middle. We put fluorine on the outside. And I'm going to fill the octets of both of the fluorines. And the reason I can do this is because it'll allow me to count by 8. So I have 8 electrons around this fluorine and 8 electrons around this fluorine, which is a total of 16 electrons, which means I have 6 more electrons. So I have 16 and I 16 placed, and I have 22 total, so I have 6 more electrons. If I put 2, 4 electrons around xenon, I have now filled the octets. But I've only used 8 here, plus 8 here is 16, 18, 20. I've only used 20 electrons. There are still 2 more electrons, but I've already filled the octets. This leads us to Rule 2b. Expand octets if you have too many electrons and the atom is period 3 or lower. So if we look here, we look at the period number, we will find that xenon, you can't see it here, but xenon is in period 5. So period 3 or lower means lower on the periodic table, so periods 3, 4, 5. So xenon is a big enough atom and is capable of expanding its octet. So we need to put those 2 additional electrons, another lone pair, on xenon. So xenon has 2, 4, 6, 8, 10 electrons around it. Again, the reason we chose xenon is it's a big enough atom to expand its octet. So therefore, we chose to expand xenon's octet. Rule 4 still applies, minimize formal charges. So we need to see, was that a good decision to expand xenon's octet, or should I have expanded fluorine's octet? It turns out you can't actually expand fluorine's octet because it's in period 2. But we can check the formal charges to see if that was a good decision. So let's do that. Fluorine wants to have 7 electrons around it, and it has, remember to count the dots as 1 and count the dashes as 1, 1, 2, 3, 4, 5, 6, 7. Wants 7, has 7, it's neutral. Xenon wants 8 electrons around it, has, count the dots as 1, count the dashes as 1, 1, 2, 3, 4, 5, 6, 7, 8. Wants 8, has 8, it's neutral. This is a good Lewis structure, even though it does have an expanded octet. Note, we had too many electrons, so we did have to expand the octet. I'm going to stop the video here, but I will add one last video where we look at ions. In the previous videos, we've looked at lots of Lewis structures of compounds that were neutral. But here I want to look at the Lewis structures of 2 compounds that are ionic. So the first one I want to look at is SO4 2-. And you probably already have a notebook out, but if not, it's a great idea to get a notebook out and treat this as if it's a lecture where you're taking notes and following along, as opposed to just watching it passively. If you watch it passively, I don't think you're going to get a lot out of it. So the first Lewis structure we want to draw is SO4 2-. The first step, of course, is to count the valence electrons. So we have 6 plus 4 times 6, and we have to decide how we handle this 2- charge. Well, a 2- charge means 2 extra electrons. So if we have 2 extra electrons, we have to add 2. So when we do all this math, we get 32 electrons. Put the least electronegative atom in the middle, so sulfur goes in the middle. We bond it to 4 oxygens, like so. Now, we want to fill the octets. Well, if we have 32 electrons and I put 8 electrons around each oxygen, that'll be 32, because 4 8s are 32. I have now filled all the octets of the oxygens. Each oxygen has 2, 4, 6, 8 electrons around it. There are 4 of them. Again, 4 8s are 32, and I filled the octets of all of these. Next, minimize formal charges. So now we have to calculate the formal charges. So in this case, we have oxygen, which wants to have 6 electrons around it, and it has 1, 2, 3, 4, 5, 6, 7. Remember, count the dots as 1, count the dashes as 1. So if oxygen wants to have 6 electrons around it, and it has an extra electron, it has 7, it's negatively charged. That extra electron makes it negative. So all of these oxygens are the same, so they're all negative. How about sulfur? Sulfur also wants to have 6 electrons around it. How many does it have? 1, 2, 3, 4. Wants 6 and only has 4. So it's missing 2 electrons. Its charge is 2 plus or plus 2. When you see a plus 2 charge, that is probably not ideal. So notice that step 4 isn't just calculate the formal charges. It's actually minimize the formal charges. So how might we minimize the formal charges? Well, it turns out we can use multiple bonds to minimize formal charges, as well as if we don't have octets. But before we do that, we need to ask ourselves a really important question. Can sulfur expand its octet? And when you find sulfur on the periodic table, it's actually in period 3 of the periodic table. So atoms that are period 3 or lower on the periodic table can expand their octet. Sulfur can expand its octet. So how does this system work for minimizing formal charges? Well, what you can do is simply take 2 of these electrons and move them here. Note that moving a pair of electrons from a lone pair into a covalent bond decreases the formal charge of the atom by 1, because essentially you have 2 electrons around this oxygen here, and when you move it into a multiple bond, you formally only have 1, because now you've given one of those electrons to sulfur. It also makes the sulfur's charge go from plus 2 to plus 1. Said another way, we want to do this twice. So we might also do it here. And when we do that, what we get is sulfur double bonded to an oxygen, like this, double bonded to an oxygen, like this, bond O. This one's still minus because we didn't change it, bond O. And this one's still minus because we didn't change it. So now I have 2 neutral oxygens, a neutral sulfur, and 2 minus oxygens. Notice that the sum of the formal charges, minus 1, minus 2, add up to the overall charge on the species. So this looks like a pretty good Lewis structure. Just to double check, let's make sure that the formal charges are right. So again, by moving this electron pair, I'm essentially taking 1 electron away from this oxygen and giving it to this sulfur, decreasing the formal charge of sulfur by 1, and also making this from minus to neutral. Let's check and make sure that's true though. Oxygen wants to have 6 electrons around it. How many does it have? 1, 2, 3, 4, 5, 6. Wants 6, has 6, it's neutral. This oxygen's the same. How about sulfur? Wants to have 6 and has 1, 2, 3, 4, 5, 6. Wants 6, has 6, it's neutral. So this looks like a great Lewis structure. I'm not going to talk about resonance here, but I do want to point out that this molecule does exhibit resonance, and we could have put the double bond in any 2 of these locations, and it would not be different. Said another way, each of these bonds is like a 1.5 bond. So this is not truly 2 double bonds and 2 single bonds. Because of resonance, these are each like a 1.5 bond. But I don't want to go into that discussion too much here, because we're focusing on Lewis structures. But I do want to point it out, if you had done the top one and the bottom one, or the top one and the side one, it doesn't matter. Any 2 double bonds and 2 single bonds would give you a great Lewis structure. But there's always a question. We're able to expand sulfur's octet, so what if we expand it one more time? What if we take these 2 electrons and make another double bond? So what you would end up with is sulfur with 3 double bonds. And each of the double bonded oxygens would contain 2 lone pairs. And you would also have a single bonded oxygen with 3 lone pairs. The single bonded oxygen is a minus charge. Now, if you take the minus charge on oxygen and you move two of these electrons into a double bond, it means that this oxygen is now going to have a 0 formal charge. And this sulfur is going to have a negative formal charge because I've put an additional electron around it. Let's check and make sure that that's true. So this oxygen was formerly negative, and then I move the electron into a double bond. It wants to have 6 electrons around it, and it has 1, 2, 3, 4, 5, 6. It's neutral. How about sulfur? Sulfur wants to have 6 electrons around it, and it has 1, 2, 3, 4, 5, 6, 7. So therefore, it's minus 1. It has an extra electron. It wants 6. It has 7, so it's negatively formally charged. So the question becomes, which of these two things is better? This has 2 minus charges, and this has 2 minus charges. My goal is to minimize the formal charge, or is make as many as possible neutral. So how do I decide which of these two is better? They're both have 2 negative formal charges. Well, it turns out that you want the negative formal charge on the most electronegative atom. The most electronegative atom is almost always the outside atom. So we want the oxygens to contain the negative formal charges. This is a better Lewis structure than this because the central atom, the least electronegative atom, having a negative formal charge is not ideal. Note that this also works for positive formal charges. If you have a positive formal charge, you want to have it on the central atom, or the least electronegative atom. You wouldn't want to have a positive charge on a more electronegative atom. So this is a better Lewis structure, not because it has less formal charges, but because it has the formal charges on the more electronegative atom. Note that for atoms that can expand their octets and they have negative formal charges, this choice is almost always the case. You almost always have a choice where you can make another double bond and move that formal charge, because it will simply move the formal charge from one atom to another. Keep the negative formal charges on the outside atoms. In the next video, I'll go over one last ionic compound like this, so we can just have another example of how to draw the Lewis structure of a polyatomic ion. In this last example, I want to go over the Lewis structure of NO3-. Now by now, you probably already have a notebook and paper out and you're taking notes as you do this. But if you don't, please do so. You don't want to passively watch this. You want to treat it like it's a lecture course. You want to be engaged, take notes, make sure you pause the video, you have these rules written down somewhere, and you're good to go. So the last one we're going to do is NO3-. In this case, we want to count the valence electrons as the first step. In all cases, when you're drawing Lewis structures, you want to do these rules in the order that they're written. So we have 5 plus 3 times 6 plus 1. Note that for the minus charge, we add an additional electron, because something that's negatively charged has an extra electron. This gives us a total of 24 electrons. Next, we want to put the least electronegative atom in the middle, nitrogen, and we want to bond it to 3 oxygen atoms. Note that 24 is a multiple of 8, so if we put 8 electrons around each of the nitrogens, around each of the oxygens, we fill the octets of the oxygens by adding lone pairs, okay, we will have used all 24 electrons. 2, 4, 6, 8 around each of the oxygens, 3 8s are 24. Counting by 8s just saves you time. It's not required. You can count the electrons individually. I would suggest counting them in pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Job 3 is fill octets. Well, we don't have octets, right? The oxygens have the octet, but the nitrogen doesn't. That's not ideal. So we have to use rule A, use multiple bonds if we don't have enough electrons. Because of resonance, it makes no difference which one of these oxygens I move a lone pair to a double bond from. Remember, I'm fixing the Lewis structure that I've drawn. It was a lot of work to draw all this. I don't want to start from scratch, so I'm just going to fix this to follow the rules. I'm going to choose, just kind of at random, this one to move the lone pair into a double bond. Again, it makes absolutely no difference which one you choose. Because of resonance, it's not really a double bond and two single bonds. When there's one double bond, it's really like a 1 1/3 bond. Resonance isn't the focus here, but I do need to point it out. So if we put oxygen, double bond nitrogen, this oxygen still has two lone pairs bonded to an oxygen. This oxygen still has 3 lone pairs, and another oxygen which also has 3 lone pairs, like so. I've now filled the octets of all of the atoms. So this oxygen has 8, 2, 4, 6, 8. This oxygen has 2, 4, 6, 8, and this nitrogen has 2, 4, 6, 8. This oxygen and this oxygen are the same, so they all have their octets. We're good to go. Minimize formal charges. Well, the first step to minimizing formal charges is calculating the formal charges. Count the dots as 1, count the dashes as 1. Oxygen wants to have 6 electrons around it, and it has 1, 2, 3, 4, 5, 6. Wants 6, has 6, it's neutral. This type of oxygen, the single bonded oxygen, still wants to have 6 electrons around it, but it has 1, 2, 3, 4, 5, 6, 7. If it wants 6 and has 7, it's negative. Note that this oxygen is the same. 2, 3, 4, 5, 6, 7. It has an extra one. So it's negative. Note that the overall charge is negative. So if we have 2 negative here, the nitrogen needs to be plus. Let's check it. So nitrogen wants to have 5 electrons around it, and it has 1, 2, 3, 4. If it wants 5 and only has 4, it's missing an electron. Something that's missing an electron is positively charged. Note that rule 4 is not count the formal charges once you fill the octet. It's minimize the formal charges. So the question we need to ask ourselves is there anything that can be done to make the formal charges better for nitrate, NO3-? And many of you may see that what you might want to do is make another double bond. So if I take these 2 electrons and I move them into another double bond, I get nitrogen double bonded to oxygen, like so. Double bonded to oxygen, like so. Bonded to oxygen, like so. This oxygen, nothing happened to it, so it's still minus. This one, I took an electron away from it, essentially. If you make a lone pair into a double bond, it's essentially giving an electron to nitrogen, which means that this oxygen has 1 less electron, therefore it becomes neutral. This nitrogen has 1 more electron, therefore it becomes neutral because it was originally positive. So let's make sure that that's the case. Nitrogen wants to have 5 electrons. It has 1, 2, 3, 4, 5. Wants 5, has 5, it's neutral. This oxygen wants to have 6 electrons and has 1, 2, 3, 4, 5, 6. So, wants 6, has 6, it's neutral. The question becomes, which of these 2 is better? This one has 2 negative formal charges and a positive formal charge. I'm just going to take this arrow out of here so it's not part of the discussion. In this case, we have just 1 minus formal charge. Which is better and why? Well, we actually violated a rule of chemistry. This violates a fundamental rule of chemistry and is not the correct answer. And the reason for this is the expanded octet rule. You can't expand the octet of nitrogen. Nitrogen is a period 2 element, so therefore we can't expand its octet. So this is a fundamental violation of the rules. This is the best Lewis structure for nitrate, even though it has more formal charges than this one. It's better because it doesn't violate the octet rule. Nitrogen can't violate the octet rule. As you may know, organic chemistry is the study of carbon. Carbon is a period 2 element. Carbon can also not violate the octet rule. This will come up in the organic chemistry class, so it's important to remember that these small molecules, like nitrogen and carbon, can't violate the octet rule, making this the best Lewis structure of nitrate. Also, an important point to point out, we have the negative formal charges on the more electronegative oxygen. We have the positive formal charge on the less electronegative nitrogen. That is a favorable situation. So even though it has more formal charges, You can't violate that octet rule, so it's the best answer. So this is all of the examples that I'm going to go over in this video series. It's very important to use these rules in practice. You're going to start to see patterns. For example, when oxygen has 2 bonds and 2 lone pairs, it has a 0 formal charge. When oxygen has 1 bond and 3 lone pairs, it has a negative formal charge. This is an important pattern to see. However, there are people out there trying to teach the patterns. This doesn't work ideally. If you follow the 4 rules, you'll start to see the patterns for yourself. Once you see the patterns for yourself, use them. But we can't just give you the patterns. Otherwise, you'll be just memorizing a whole bunch of patterns, and it won't work out that well. If you follow the rules, you practice enough, and you see the patterns for yourself, use them. That would be great. So you can practice on Alex or any other homework system that you have, or the textbook or whatever, but it is really important to practice with this stuff now that you have the tools that you need to draw Lewis structures.